Yeah, I'm very excited to introduce our last speaker for today. We have heard already a lot about AI agents, and now we get a really deep dive. So it's my pleasure to introduce Bang, who is a professor at computer science at the University of Montreal and an expert for AI agents. And he will tell us all the details we need to know. So thank you very much.
Thank you very much for the introduction and for the invitation. So this is a beautiful city. That's why I used a photo as the cover. And thanks for attending this session. So I'll talk about advanced challenges in foundation agents, which is basically built on one of our recent survey papers. So first I will introduce the concept of agents and foundation agents. Then I will introduce two of our recent work, which is about the core capabilities of an agent, like the reasoning capability and the memory part. And lastly, I will talk about the applications of applying AI and AI agents for material science applications, which is about one is called MedExpert and another is called MedAgent. So I have more content to cover than within the time, so I will make it quick. So first, let's say, how many of you have experience about agents? Okay, it's not bad. Yeah, then do you know which of these are agents based on your impression? So for example, robot webcam agents, right? Software, is it an agent? No. And health tracker? Yeah, so this is a very basic question, right? So what is an agent? If you check the textbook from Still Russell, so it says that an agent is anything that can be viewed as perceiving its environment through sensors and act upon the environment through actuators. So basically, if I ask ChatGPT based on this definition, you will get such an answer. So the robot welcome, human, chatbot, thermostat, and so on, those are agents. And camera and plans software, they're not because they are more reactive instead of active, right? And also the health tracker is kind of borderline. And human beings have want to build smart things, right? So maybe even smarter than ourselves. And there are so many different movies, TV shows. So people imagined about different kinds of future, like the AI in just a pure virtual assistant or with an embodied different robots, right? And some of them are quite powerful. They can augment the intelligence and capability of us. And some of them are quite evil, which leads to a disaster future. So it depends on how we carefully choose the way, how we develop the technique and incorporate it with human society, right? And a lot of articles say, okay, this year, the topic of agent is very important. So people say this is the year of AI agents. So we want to know, where are we right now in the landscape of agents research, and what is the next? What are the promising research directions from now? So we can see we have already have very powerful language models. We have very impressive reasoning capabilities, but still we have limitations in terms of the safety, the trustworthiness, multimodality, empathy, embodiment, and so on. And we want to build a unified framework to better coordinate different capabilities, different components for AI agents. And we want to improve the core capabilities like the lifelong learning, the reasoning ability, emotion grounding, multimodality, and so on. And that's why we conduct such a large-scale investigation about this topic. So this is available on arXiv. And also, we are releasing a new version by the end of this month or early next month. So if we recap this definition about agents, we will see. So the cognitive part is not so clear, right? We only know that we take the input perception and making decisions about it to decide the actions, but how? So we need a framework to guide us about what to check and how to design the framework. So let's check the only model we know about what we think is true intelligence, like the human brain. And if you compare a human brain and the current AI agents, we both have pros and cons, right? So let's say the good part of human brain, we are strong in continual learning, and AI models are relatively more task specific and data driven. We are definitely better in terms of the energy efficiency and generalization, embodiment, and so on, and memories, self-awareness, and relatively AI agents are not so strong. But also, like AI agents has their own advantages, right? They have very high speed and precision about many modalities, and they have strong memory accuracy because they can scale up easily, right? And they're strong in multitasking and parallelism, but this is the nature of their model architecture. And they have access to external knowledge. They read so many stuff during the training, while our human beings can only read a tiny portion of it. And they have no fatigue or emotion drift. So by comparing human brain and AI agents, we want to know what are the good parts of both worlds and how to bridge in the gaps. And if we check like the research landscape and the core capabilities of human brain, we can consider, let's say, categorize different capabilities in different levels. Let's say 3 levels. L1 is well-developed features or research topics, and L2 are partially developed, and L3 is kind of underexplored. So if you check like the language comprehension, so this is quite strong, right? Because this is what language model is doing. Also visual perception, computer visions, and relatively like many other topics, planning and reasoning, sensory integration, reward learning, attention control, spatial perception and navigation, and so on. Those are all very hot topics, but still we have significant research rooms there. And also a lot of like dark matters in the zone. Let's say the L3 underdeveloped. For example, the different types of memory mechanism, episodic memories, cognitive flexibility, working memories, and emotional grounding, processing, and learning, tactile perception, and so on. So we can say that there's still a long way to go, right? So while some of the topics are quite hot and well developed, there are still many others we haven't tackled so much. And people are working on different topics like learning, planning, workflows, the design of agent memories, tools, APIs, and different the protocols like agent to agent, MCP, and so on. So we want to have a more modularized, unified framework to better connect different topics. So let's talk about what we call a foundation agent. So these are some notations, but you don't need to remember them. So let's check this figure. So we have, like from a high level, it's quite consistent to what we know. You have perception from the environment, right? You have actions to take. And what's more fine-grained is within this cognitive part. So specifically, we define what we call the mental state space. And we define several key elements there, like sub-mental states, like the world model, as introduced by Dr. Ziting. And the memory part for like memorize the past experience and reward shaping, the emotional grounding, and the goals and so on. So we consider all these are some critical parts for the internal mental states. And then we further define what exactly is cognition. So let's say, starting from the environmental state, you have asset at time step t, right? Then for the observation, you have perception function, which takes the current environment as of t. And depending on your previous internal mental state, you will get the observation, which means that even for the same environmental state, it depends on your current status to pay attention to different parts of the mental state, to the environmental state, and got observations, right? And then for the cognition, we can consider it's like based on your previous mental state, your past action, and the current observation. You're updating your mental state and also decide the action. So basically, it means that you are doing learning and reasoning. So for learning, we consider it's like a more long-term effect, which is about updating your own mental state. So it's like taking the last mental state and your last action and the current observation, you're updating it. Basically, the action and observation forms the message about your experience, right? And reasoning is more about making decisions about the context, about the current stage. So which means you have a reasoning function which takes the current mental state and decide about the action. And finally, you need to execute this action in the real world, right? Because different types of actions, they have different difficulty levels. For example, if you are just calling an API, so it's quite easy. You just call the function with the code. But if you're doing some more continuous control, let's say for embodiment for robots, the difficulty is more challenging, right? So that's why you have action execution. And finally, based on the executed action, you will have impact to the environment, and it will transit to the next state. So basically, in this framework, we want to make it clear what are we caring about. We define the mental states, and we define the framework of cognition, which consists of the learning and reasoning. Do we have any question until now? Okay, let's continue. So the next question is what do we hope? What kind of properties we hope that an agent will have? So we call a foundation agent is an autonomous adaptive intelligent system designed to actively perceive the different signals from the environment, continuously learn from the experience to refine and update its structured internal states, and then reason about the purposeful actions, both external and internal actions. For example, let's say if you have some virtual mental actions to take, like planning about current task and so on, so to automatically navigate towards the different objectives. So make it more brief. Basically, we want to emphasize two capabilities. The first is that we consider it is a fundamental generalizable intelligent unit. And the second is they can be combined and collaborate to form powerful multi-agent systems. So the reason we emphasize more about the multi-agent structure is because even if you can build a single very powerful agent, we consider it's not so effective and efficient to solve complex tasks, right? Because a multi-agent design naturally mirrors the human society's organization, so it can better decompose the task and solve it in a more manageable and effective way. So to achieve such kind of foundation capability, you need to have some core functions, right? You need to be able to have multimodal perception or cognitive adaptations to different tasks and environments. You need to perform goal-driven reasoning and conduct purposeful actions. And finally, you need to be able to collaborate with each other and to form multi-agent systems. And we also discussed the connection to other existing theories. So basically, what we want to emphasize is that it doesn't contradict with existing theories, but trying to combine the different views. So next, I want to talk about the different components of an agent. So previously, I included different parts, but I think we don't need to cover all of them. So if you want to know more, let's say about other parts, let's say the emotion, the reward, actions, and the perceptions, you can check the survey. So here we want to talk about the reasoning part and the memory part. So reasoning is the core cognitive capability of intelligence, right? So let's say we define the reasoning as infer the next action based on the mental state. So biologically, we say that human beings have both fast intuition, what we call the system 1, and also deliberative analysis, like the system 2, right? And from the AI perspective, it can also combine step-by-step reasoning, which more emphasize on the depth of the reasoning process, and also parallel reasoning, like about the breadth of the reasoning process. And if you check the diagram of how people train the DeepSeek R1, so this is quite a complex structure, but basically, let's check this one. It's more simplified version. So it is divided into 4 stages. The first stage is a code start stage, where the model is begins with high quality data and chain of thought reasoning examples. So you can let it have some initial reasoning capability. And the second stage is reasoning-oriented reinforcement learning stage, where we conduct large-scale reinforcement learning and focused on the reasoning tasks. And then you further perform rejection sampling and supervised fine-tuning stage, where like you can use the model to generate new data and retain the high-quality paths. And finally, you continue with the fine-tuning. And finally, you can apply the reinforcement learning to improve the helpfulness and harmonies. Right? Basically, you align the model with human values to make it more safe. So during this process, the chain of thought reasoning is being used extensively. We can consider chain of thought reasoning is the most fundamental and basic, let's say, the depth-oriented reasoning methods. So you start from some nodes, and you continue with this step by step. So basically, increasing the depth during this reasoning process. So you can see from the left figure, basically, chain of thought reasoning means previously you have the question and you have the answer. Now you give the model a new question. You are expecting the model to directly output the answer, right? Without any intermediate process. But chain of thought reasoning means you show it the process to solve the task step by step. And similarly, the model can learn from the in-context example, and it will also solve the new question with a similar process, which is the green part, you see? With this intermediate process, the model can get the correct answer instead of the wrong one. And similarly, there's another idea called self-refinement. Basically, it means that it iteratively improves the output through self-refine. So basically, at each step, you can self-reflect on the current process and improve your next step. So this is a sequentially breakdown for the complex tasks. And it is interpretable step-by-step process, but it also can be slow and prone to error propagation. Aside from such a depth-oriented methods, people developed many different reasoning paradigms. Right? So basically, it means you are expanding the searching space, and you're searching the searching space with different paradigms. For example, previously, if you are doing this chain of thought reasoning, it's like a single chain, right? And naturally, you can, let's say, expand it into several parallel chains, which means you explore several different solutions in parallel and see, okay, which one can work out. And more generally, you can generalize such kind of multi-chain structure to tree structures or even graph structures, right? With more and more structure, you are making the reasoning process more robust. You are trying to achieve a more optimized solution and reduced uncertainty. But it has a price, right? With more complex structure, more state management, naturally you will have more computational costs, right? And requires pruning to reduce the unnecessary searching space. There are many other paradigms like model-based reasoning. For example, you combine Monte Carlo tree search with process reward models and reinforcement learning-based reasoning frameworks. There are also test time scaling, which is quite hot this year. Basically, people combine with reinforcement learning to improve the scaling during the inference process. And also planning with tools and memory. This is a more agentic way, right? You can have access to external resources to improve this reasoning process. And the new paradigm is reasoning in the latent space. So if you consider chain of thought reasoning, it's like before output the answer tokens, you have some intermediate reasoning tokens. Basically, these tokens are the intermediate process to infer the final answer. So the idea of reasoning in the latent space is, so this figure from the Coconut paper. So it means that you actually don't need to output the language token in the language space. So let's consider you have many continuous tokens in the latent space, right? So previously, maybe you need to output 10 or 20 different language tokens, but now maybe you only need to infer for 3 steps in the latent token. So if you think about whenever you are decoding a token, you need to perform classification over the whole vocabulary dimension, let's say more than 30,000. But now without such a decoding process, you can actually improve the efficiency, right? So this is the latent reasoning paradigm. So let's see, can we combine the fast heuristics of system 1 style reasoning with deep reasoning, like the system 2 style, right? So that's what we call it system 1.5 reasoning. So traveling in language and latent space with dynamic shortcuts. So you can tell from the title, it's like we want to combine the advantage of both worlds, right? So let's check what's the problem with the current reasoning. So if you check about chain of thought reasoning, it improves the model reasoning process, but it's also inefficient. So the many steps, like it doesn't actually contribute to solving the task. And also models often overthinking. So let's check this example. If you ask this open source model, the QW 32 billion model, you ask it like, what is 2 plus 3? Like for human beings, we will directly answer is 5, right? So it's a quite simple question. But for this model, it will like try different solutions, solution 1, 2, 3, 4, 5. And then finally, it will tell you with confidence, okay, the answer is 5. And actually, this cost like 901 tokens for such a simple question. So you can see many of the tokens are not necessary. It's quite inefficient. And if you check different reasoning paradigms, so for paradigm B, the chain of thought, as we have shown, like it's token by token decoding for the reasoning process and for output the final answer, right? And for early exit, so basically it means that, let's say, if you have a very deep model, maybe with 20 or 100 layers, you don't need to actually go to all the layers for each step. Some steps are easy. You maybe just need 2 layers to predict what is the token. Some are more challenging, so you need more depth. So in this case, you're turning this inference process from a fixed depth into a more flexible way. So that's what we call the early exit. This can help improve the inference efficiency. And for the compressed latent reasoning, this is what we have just shown. So basically, you don't need to actually output the reasoning tokens. You just need to like perform continuous reasoning in the latent space. And extra latent reasoning is like sometimes you can inject some special tokens to control the reasoning length. Let's say to pause to conduct a deeper reasoning process. So a more natural way is like you can actually, yeah. 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 So basically, let's say when you are doing shuffle reasoning, at each step, you need to output the reasoning token. But if you are conducting continuous reasoning, you just need to continue with the next step to get the new token. And then, so basically, when you are trained with the data, you already have the token, right? You don't need to decode the tokens, but it will shrink the decoding process. But all you need is actually just the final answer. So that's why for this latent reasoning, we can like skip all those intermediate tokens. So for more details, you can check the coconut paper. This is a quite classical work. Yeah. So comparing to all those paradigms, that's why we want to conduct what we call the system 1.5 reasoning. So let's say if you reduce the vertical reasoning depths, you differentiate, okay, at different steps. Some of the steps are easy ones. Some of them are more challenging ones. So it may take 1 layer, 2 layers, 100 layers. But we can actually also have some horizontal shortcuts, right? So it's like we are trying to differentiate different cases. So basically, we introduce 2 dynamic shortcuts to enable the more flexible latent reasoning paradigm. So the depth shortcut, you can consider is the same for early exit. And for the horizontal shortcut, it skips travel steps trivial steps by reusing the hidden state from the last step to the current ones. So what does it mean? So basically it means that like at each step, so let's say at each step, you have 3 different options. One option is, okay, I already know what is the answer. I can start decoding the answer token, right? I will stop here. So this is NERSC. For the second option is, I still need to infer with more depth. So I'm now at layer L. I need to continue with layer L plus 1. And for the third option is, okay, for this time step, I'm already clear. I need to continue with the next time step, but I haven't known the answer yet. So I need to have one more like token in terms of the like x horizontal scale, which means I need to skip from time t to time t plus 1. So this can be naturally incorporated or implemented by a gating mechanism, right? So that's why we have such a gating mechanism. At each layer, at each time step, you can decide which pathway you want to go. And naturally, we can train it with such a combined training loss. So to implement such a mechanism, we need to solve 2 challenges. The first is the original language model, it is trained in the language space, right? You don't have the supervision for these latent alignments, latent signals. So basically, we conduct this latent alignment. So let's say you have a teacher model and you have a student model. This student model, you don't need to decode the reasoning process. So you need to align the latent space with the teacher model. So this gives you the language to latent alignment training. And the second is you need to differentiate which steps are the key steps, which steps are some easy steps, right? So basically, we utilize an existing technique called atomic thoughts. So the idea is like you have, let's say you have some question answering data, you can decompose it based on the logical structure. Let's say pass it into a tree structure. Then all those root nodes are some key steps, and all the leaf nodes, they are like following these root nodes. So in this case, you can also have some label data to decide which steps to like conduct fast reasoning, system 1 style, which steps are like more deep reasoning, system 2 style, right? So by combining this, we train the model. So we take a pre-trained language model and we change the structure and combine with those different labeling by basically this 2-stage training, right? First the alignment and then the shortcut learning. So what we found is that, so if you compare with these different baselines, so actually for many of the baselines, they need 20 to 40 steps for the intermediate reasoning process. But now we only need to take 2 to 4 steps. And we actually speed it up by like almost 20 to 40 times. So here is a text summarization. So the main finding is that our model is superior efficient. So it achieves like up to 55 times on the strategy QA dataset. And it has competitive accuracy compared to the original chain of thought reasoning. And it also outperforms on another dataset. So basically, like it means that we used much less hidden tokens and we improved the inference efficiency a lot, and we achieved similar or even better performance compared to original chain of thought reasoning. Another benefit is that like once you have trained the model, you have 2 parameters to control. One parameter is the lambda depth. So basically it's a threshold value between 0 and 1, right? Which means, let's say at each step, you need to have how much confidence to stop here, or you need to continue with more depths, right? And then lambda step controls like how many latent steps you want to use for the reasoning process. So naturally, if you use more steps, or if you set the depth threshold value higher, which means you have a more strict condition to stop the reasoning process. So that's why, let's say, if you increase both of the parameters, your performance will be increased. So let's say if you have already fine-tuned such a reasoning model, you want to deploy it into different tasks. Like for some scenarios, you're mostly dealing with more simple questions. For some other environments, you're dealing with more complex questions. So in this case, actually, you can adjust these two parameters without fine-tuning your model again, right? So to summarize, in this work, we propose what we call the system 1.5 reasoning to dynamically allocate the computational resource across both the model layers and the decoding steps. And we enable efficient latent space reasoning and achieved high performance with a lot of speed up. So our next step is we want to integrate memory, latent memory, and reasoning as a cognitive engine for broader agent applications. So before I move to the next part, do you have any more questions? Yeah. 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 So you mean after we go back, what do we do, right? So basically, let's say if you continue in the vertical direction is at the normal transformer, but we also have the horizontal shortcut. Basically means that we copy the latent vector at the previous time step, and you can apply a simple projection layer to transform it like this. So in this case, like previously, need to go back and again and pull up the next time step. But now we submit a very lightweight everything based on the previous time step. It's quite easy to use the what we at the same level. That's why it's okay, so let me continue. So next, I want to talk about the memory part. So first, we need to know that large language models are stateless. So let's say if you have an input for the model, it will give you an output. If you have a new input, you will give it another output. But actually, it doesn't have any memory about the past interaction. So if you check how it's implemented for the chatbot, what people are doing is it will accumulate the dialogue history. And whenever you have a new input, it will connect it with the history and to send to the model again. So this is a fake memory implementation, actually, right? So that's why it's stateless. And naturally, an external memory module makes the language model stateful, right? So you have, let's say, an attachable memory to buffer the your thing over time. So it will enable the model to have continual dialogue, personalized agents, and perform long horizon tasks. Basically, it stores your experience, your past history. And human memory has a hierarchy. Like, let's say you have long-term memories, short-term memories, sensory memories, and for each category, maybe you can further divide it into more fine-grained types. So here we can talk about like two core problems: the representation of memory and the life cycle. So for the representation, so let's say the sensory memory. So it's about the initial encoding and the transient retention of your sensory input, right? You have some raw signals, you need to acquire it. So here the key is like how you can perform attention-based filtering to reduce the noise and retain the valuable information, and how you can deal with multimodal inputs. So to perform effective multimodal encoding and align with different signals. And for short-term memory, it's about temporary storage for intermediate task-relevant data. So here you need to manage the context, and you have to implement some kind of working memory for the current context, for the current task, right? And for long-term memory, it's more about like a long-term durable information story. For example, let's say if you have an agent keep interacting with the user, you gradually establish the profile of this agent, this user. So basically, the agent knows better about this user. So here we need to have semantic and episodic memory integration, and we can understand, for example, different procedural memories and store it and utilize it when solving different tasks. And memory life cycle is like from the acquisition to its utilization. So basically for the acquisition is about capture the signal from the environment while filtering out the noise to avoid cognitive overload. And for encoding is about transform the filtered sensory input into more structured, robust internal representation. And for derivation is like you want to discover more meaningful latent information, right? For example, you can, the most simple way is you can conduct some reasoning like summary process to condense the information. Or you can also conduct some self-reflection process to drive the unknown information, which is not explicitly mentioned in the dialogue. For example, based on the dialogue, you can infer, okay, what is the job of this person? And retrieval is about when you need, based on the current context, what kind of information you actually want to retrieve from your past experience, which part of them are actually useful. Utilization is about, let's say I give you the relevant piece of information. How are you going to use it? Are you going to use it for reasoning, for planning? Are you just using it as an in-context example or not? So there are different ways to utilize this model, this data. And there are two different types. Like it can be some explicitly encoded data in the storage. For example, vector database, right? Or relational database or graph structures. It can also be some implicit way. Basically, we are talking about the neural network ways. So they have their own pros and cons. For explicit memory, it's quite editable and it's quite interpretable. Basically, you preserve original information by storage, right? But it's also, you need to have extra latency and storage. It's hard to scale up. And for implicit memories, so they are encoded in the ways. So there's much lower latency, but they are also harder to update. For example, you need to conduct what we call the model editing to inject or revise the information in the model, right? So there's a trade-off, what we call the retention and retrieval trade-off. So if you have some kind of explicit memory, you can reliably retrieve the information because the information is stored, preserved very well with the raw data. But it's hard to scale. So there is a storage and management problem. And for implicit memory, so maybe the information is not encoded so well. So you have the retrieval reliability challenges, but it's much more friendly for the storage and management. So our work want to improve both. We want to maximize both the retention and the retrieval. So specifically, like how we can simultaneously maximize this retention and retrieval while keeping the external storage minimal. So the paper is also available on arXiv. So let's consider two different ways to use memory. One is what we call the generative memory. So basically, it means if you have a neural network stored all the past information, past interaction and history about a user. So when you ask it some question, so basically, based on the understanding about this user, the model can generate the output. So in this case, the retrieval is conducted by a generative manner. It's retrieved from the latent space. And for retrieval, it's like you have a retriever, which maybe it doesn't know this user, but based on the current query, it can retrieve from a very large scale external storage, right? So in this case, like it's more general to different users. So basically it means that a generative memory model knows better about a specific user. It can provide more personalized in-context recommendations or information. And retrieval is more like, I would say, it provides best match search, but it's not best fit help because it knows less about this user. So we want to improve the implicit memory mechanism. So the idea, the first idea is that we can interpret a memory as compression. So the retention is like you compress original long context into a compressed memory format. And the retrieval is like the decompress on demand based on your current query rate. So this makes it naturally a dual task. You have the X to Y, and you want to recover X from Y. And that is like, well, we can utilize the reversible memory network, reversible neural network. So reversible neural network is an existing topic which has been researched by many people. So basically, you can check this figure. So let's say you have from X to Y. If you have two modules, F and G, and you define the relationship based on this, you can actually calculate Y from X. You can also calculate X from Y based on another formulation. And there are research works, like let's say you have a transformer. The original transformer is not such a reversible architecture, right? But you can have two adapters, one to represent the F function, another to represent the G function. And similar with this work, you can actually turn a transformer into a reversible architecture by perform perfect parameter efficient fine-tuning with these two architectures. So why we need this? The reason is that to have a good memory network, first, the network should be a good language model. It needs to be able to understand the language and generate it. So we don't need to train from scratch. Instead, we want to take an existing transformer, let's say Llama or any other open source models, and turn it into a reversible transformer and fine-tune it to be a memory network. So that's what we want to do. And what kind of data we want? So as we said, if you consider it as a compression decompression problem, you can take a long piece of documents. Let's say you compress it into different granularity, from document level to paragraph level to sentence level, and finally to entity levels. So in this case, the original data is compressed into different hierarchy. And this can be done by an Oracle model, for example, GPT-4, so that you can get a lot of context query pairs. They are in different granularity, like doc to paragraph, paragraph to sentence, and sentence to entity. And further, you conduct some filtering to preserve only high-quality data. And finally, we have such an architecture. On the left, you can see this is the data. So you have different granularities. So basically, you have both long context and short queries. And in the middle, this is the model architecture, which is a reversible transformer network as we have introduced just now. So basically, you don't need to fine-tune all the model. You just need to fine-tune the adapters. So basically, it's a parameter efficient fine-tuning. And also, we designed what we call the memory token. So the memory token, like for each segment, you prepend the read token and append a write token. So in this case, it helps you to like compress the context into a condensed memory token. So in this case, you're not forgetting information, right? So it helps us to scale to arbitrary long conversations without the semantic drift. So you can consider it as the token like the CLS token in the BERT network, right? In BERT network, you have the input two sentences or one sentence. You have the first token, which represents the whole sentence. So this is a similar idea. And you can train such a model with a combined loss function, the compression from long to short, expansion from short to long, and the consistency between the original context and the reconstruction. So basically, our experiments show that such a memory network sets new sort of performance across different datasets. And we also test the retrieval performance in both in-domain setting and out-of-domain setting. So we have better compression, and which leads to better retrieval. And the out-of-domain still lags, but also the ranking remains consistent. And lastly, let's say we take this R3 as a memory module, and we plug in it into an existing agent framework to see, okay, how it performs as a standalone memory component. And we compare it with several other implementations like the memory bank and memory rack. So in terms of different metrics, so here are 5 different dimensions. We have improvement compared to those 2 baselines. And basically, the application study says that, okay, many key designs helps a lot, like including the hierarchical compression data and the high quality pairs and the virtual tokens design and the backward path or the cycle loss. So do we have any questions? Okay, we have introduced two, yeah. Yeah, so basically, let's say if you consider a virtual token, let's say for the forward pass, you are reducing a long context into a shorter and shorter ones, right? So in this case, you can consider, okay, this, what we call the reading token in the forward path helps us to compress the long context. Originally, maybe you have 100 tokens and the output is 10 tokens. So you need to have some like condensed token to represent the whole context. Otherwise, you lost the details, right? And when you're backward, it's like you need to read from those compressed tokens to reconstruct the original information. Right? So that's why we have that kind of like memory tokens to compress the information and preserve it with much less tokens. And also, it helps us to scale to arbitrary long conversation rate. Let's say if your original context window of your transformer is, let's say, 100 tokens or 1,000 tokens, but now you have 10,000. In this case, you can compress this very long context into more like such as compressed memory tokens. So you can reduce the context length. Okay, so we have talked about the reasoning part. We have talked about the memory part. So for this memory part, we want to further integrate human-like memory dynamics, like the recall of memory, abstraction of different concepts, and adaptive forgetting to the existing AI agent systems for more powerful and reliable performance. So the last part is the application part, how we can apply different AI agents for material science. So the first work is in this year's ICLEAR. It's called MedExpert, Decomposing Materials Discovery by Mimicking the Human Expert. So how many of you are working in this material domain? Okay, good. Yeah, a lot actually. Yeah, so basically here, our goal is we want to generate stable crystal structure that matches user-defined property constraints, right? So for example, if you have such a problem, I'm looking to design a new material with the following property, you have this. Sorry, what warning is the recording? Recording? Okay. Yeah. So basically, you describe your need, right? Which is specified by several properties, and hope that the model can generate the crystal structure in the CIF format for you. So why AI can help here? Because the traditional methods, they are expensive and slow, right? If you conduct the DFT simulation for one material, it may take hours to days of compute. And for existing like methods, for example, the crystal LM, it directly outputs the structure from text. There's no chance to revise or refine the result. And for the second method, it has a weak grounding between the properties and structure. And the third method is like, it's great for unconditional generation, but it's hard to condition on properties. So our idea is quite intuitive. Like, let's say, if you want to design some material based on some required properties, you're not start from scratch, right? You have some prior experience, you have knowledge. So the idea is that maybe we can retrieve some existing material and identify the gap. How far away is it from what we need? And based on the reasoning, the knowledge of the model, we want to bridge the gap by some intermediate actions. So that's why you have the three stage. You retrieve the relevant existing memory, you transit the existing memory to the target structure, and finally you generate the output structure in text based on your actions. So in this case, you can have property-driven generation, supports iterative refinement, and reduce hallucination because you have grounded reasoning. So this is an overview. So let's say it's long text, I want to read it. So basically it shows that, okay, the user is describe her needs. Then you have the retrieval stage, which identifies a material which is quite relevant to what you need, but still not the target. And then the user asks it, okay, what is the gap? So which path you want to modify to meet the property requirements, right? And the model will reasoning about the actions to take during this process. And finally, based on these actions, the user is asking the model to generate the structure in the CIF format. So actually, like the model will directly output the LX representation, and then you can transform this LX representation into the CIF format using open source tools, right? So first, for the retrieval stage, basically we trained a dual T5 encoder for the property and structure descriptions to embed both into a shared latent space. So the property description here includes the composition, band gap, formation energy, and so on. And for the structure description, it's auto-generated using this RoboCrystal grapher open source model, and it translates the CIF into human-readable text. And this shows the whole pipeline, right? So let's say you have this retriever. So based on the GPT T5 encoding, you can conduct retrieval by similarity, right? And then you can ask an oracle model. At that time, GPT-4 is the best, but now you have better ones. So basically, it asks, okay, I have this material, I have these properties. What kind of gaps? Right? You have some, let's say, from your data set, you know what is the ground truth material. And you have another material which is retrieved from the data set. So it's quite easy to ask the model to compare these two materials to generate the faithful like transition path, right? And based on this transition path, actually you can fine-tune an open source model, for example, Llama, to learn such a generation process. And also, once the model understands the transition path, you can continue fine-tune the model to generate the target properties, the target structure in the LX representation. So after it, like it will be transformed into the final CIF structure description based on the PyMedigen library. So any question about this process? Okay, yeah. So basically the core is how you can utilize the existing model's knowledge to generate such kind of reasoning data, right? And then based on this reasoning data, you can fine-tune open source model to learn this reasoning capability. And in this case, like once you have new requirements, it can reason in a similar paradigm and also generate the new materials. So basically, application study shows that such kind of chain-of-thought reasoning has improved more than 20% performance in condition satisfaction. So this shows the prompt we're using. So you have two materials, the source and target, and you're asking the model to generate the transition path, right? And the LX is lattice vectors plus the atom position descriptions. And it can be converted into the CIF representation using the PyMedigen tool. So the final material like is well properly aligned. So we construct our data using the combines like both the nomad and the materials project. So this is the comparison for unconditional generation. So basically we see that the MedExpert outperforms the Crystal LM, CDVE, and MCHAC models, and is especially strong on the distribution matching between the ground truth distribution and the generated distribution. And this is for the conditional generation, which means you're giving the property requirements and ask it to generate material which satisfies these input conditional properties. So we can see that MedExpert meets user constraints better than other baseline models. And also, you can see for different So because we are using different open source models, right? So the choice of the open source model and the ground truth model for generating the like chain of thought written data also impacts. And this is a case study, so we can skip it. So basically, like from this work, we are bridging language models capability with scientific reasoning. So we paved the way for interpretable, controllable material design using the foundation models. And we will further explore closed-looped material discovery, like integrate the synthesize and test and refinement, and also using active learning or reinforcement learning to propose or post-process like the structures. And also you can see such a paradigm is not, it is quite general, right? It's not limited to material science. So you can generalize it to other domains, for example, drug discovery, protein engineering, and so on. So the next work is called Accelerated Inorganic Materials Design with Generative AI Agents, which is built upon our prior experience we learned from MedExpert. So the design of inorganic material with specific property is quite crucial for different domains. Like you have structural materials, you have functional materials, energy materials, and sustainable materials. So they are served for different purposes, right? So basically, typically you have a generative process. Given the input properties, you are generating the structure. Yeah. Oh, yeah, you can also ask. Yeah. Here? Yeah. Yeah, you mean the ground truth pathway generation, right? So I think I don't include an example here, but basically, like the idea is you have a target structure, you have a retrieved structure. Usually, the retrieved structure is not as perfect as the target was, so they have the gaps, right? Then you're asking the model how you can turn this retrieved structure into the target structure. What kind of modifications you need to conduct? For example, you're replacing some function groups, you're replacing some chemical elements and so on, right? There are different granularities in terms of this modification. So in this case, because all those large commercial models, they are pre-trained with a lot of disciplines, right? They have the knowledge about chemistry, about biology and so on. So if you're given the source and target, they are capable of producing such a transition path, right? So now let's say you have drugs. You can also describe your drugs with the structures, right? And you can ask it to compare the difference. Yeah. 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 I don't remember the numbers actually, but you can check the paper for details. Yeah. Um, yeah, we trained a dual T5 encoder, so you can just calculate the cosine similarity of the encodings. Yeah. Yeah, yeah. Yeah, yeah. Because we are encoded with work, so and it's stored in work database, right? So basically, whatever method you can use for rack, right, for this kind of retrieval, you can use it. Yeah. So basically, this is a quite simple implementation of rack. So if you have like a more advanced solution, that's definitely applicable. It's not the focus of this work. So that's why we just use a very standard rack. Yeah. Okay, let's continue with this work. So usually you generate the material, right? And then you use DFT simulation to predict the property to see, okay, whether it matches with our requirements. If not, let's continue with this loop. And diffusion model is used for materials design. So basically in this work, the MetaGen, so they have a diffusion model with graph neural network as a denoising network that jointly generates the lattice vector, atomic coordinate, and atomic species. So it uses a class fire-free guidance was used to guide the generation towards a material with specific properties. So this is what MetaGen has done. And it also works using language models, right? For example, MetaExpert we have just introduced, and the Crystal LM. So we can see, okay, those models, they can generate materials in graph, in text, but they're hard to precisely meet the target property, and the exploration is still limited by pre-trained knowledge of the models, right? So what we want? So we can condition the generation on these properties, and we have those limitations. So can we make the system self-driving to pursue target properties or explore a broader material space beyond the training data? So basically, we want to generate more diverse properties, right? More diverse materials. And also, they have poor interpretability. So can we make the system interpretable enough to uncover material design principles? So basically, we hope that the generation process is you can generate novel designs. And in the meantime, it can be also interpretable by human beings. For example, let's say if you take a diffusion model, it's like you take the input text, the description about your properties, and it output the structure magically. If it's good, you're lucky. If it's not, you need to do it again. There's no explanation about why such a structure is being proposed, right? So how can we achieve a framework that can explore broader material space in a self-driven way with sufficient interpretability? This is what we want. So the idea one is we want to navigate in material space through the iterative refinement. So basically, instead of a one-time generation, we hope to incorporate feedbacks from the last iteration and continuous iteration, right? Basically, you learn from your past failure and you adjust the generation process. So how to explore materials in a self-driving way with sufficient interpretability? So we need LMs, right? You need to explain how you actually do the reasoning, how you infer the structure. So let's say you have the property, then you use a language model to generate the discrete material composition with explicit reasoning, just like how we did in MetaExpert, right? And based on the reasoning outputs, basically it proposed a composition plan. Then you take in this plan for the diffusion generation model, and it will generate the continuous lattice vector and atomic coordinates. So you can see in the MetaGen, your input is your property. You have this diffusion model, and it will directly generate the structure. But now you're turning this input with a reasoning process to generate a composition plan. So in this case, actually, you have more detailed information about what you want, right? Because this is conducted by the reasoning process. So in this case, you're combining the strengths of both the reasoning capability of language model and the structure generation capability of the diffusion models. And how to explore broader material space in a self-driving way with sufficient interpretability. So we want to make it novel, right? So as we emphasized as well in the MetaExpert, human beings relies on knowledge, right? We're not starting the generation from scratch. We rely on knowledge. So naturally, in an agentic design, you can integrate external knowledge, you can integrate external tools. So basically in this work, we include both short-term memory, which remembers the recent proposal and feedback, and long-term memory, which records past successful tries and reasoning. We also include the periodic table, which suggests chemically related elements and knowledge base to provide insights from non-composition property relationships. And of course, in your domain or in your task, you can design what kind of external material or external resource you need, right? So how this work? So basically, it has 4 stages in a loop. So you're given the current situation, the language model will select a tool. And then in the second stage, the LM will generate a proposition based on the tool and based on the previous cycle's feedback. And based on the proposition, the diffusion model will generate the material structure, right? And you compare this structure with the input requirement, and it will generate the feedback, and you continue with this loop. So here is the planning. So let's say the prompt for is like your objective is to propose some material. So to do so, you first need to assess the current situation and determine the optimal plan for your next step, blah, blah, blah. And you're provided with these tools, and you have some planning history. Okay, then like we have talked about this. These are different external tools. So basically, the language model knows what it has already done in the past history, right? It also have access to the tools, have the requirement from the user. And in stage 2, it will generate a proposition plan based on the inputs. So for example, here, it selected the short-term memory, it retrieved the relevant information, and based on this information, so it further generates the new composition, also with reason to explain why it proposed such a plan. And then you take the diffusion model. The diffusion model take the composition plan as the input and generate the 3D structure. And finally, you have the property evaluation. To, for example, you train a graph neural network to classify the property, and then you can compare this property with your input properties and to generate the feedback. And then you continue with this cycle process. Yeah. Yeah. You mean what's that?
Well, the way I describe that is that
Yeah.
they can just
Also, here we don't synthesize the material with a real lab, So we just predict the structure, and then once you have this structure, you have this trend graph neural network to predict the property. So in this case, all of these are conducted by a model. So you don't need to actually synthesize the material in the real world and test, okay, what kind of properties you have. Yeah, so basically you can evaluate how good are the whole process by like taking the data set to see what is the accuracy. Because we are from computer science, so we don't do such experiments, right? We do all of the experiments in computer. Yeah, actually, I'm collaborating with another professor. He has a lab to synthesize the material, so we are going to do such kind of experiment actually. Yeah, but usually for in the computer science department, we do all this virtually. Yeah.
Sure, this is great.
Yeah. Yes. Yes. Yeah. Yeah. Yeah.
And there is often a stochastic element that the model will generate. I'm curious if you guys have experienced like the spread in terms of reproducibility, I guess, from one input
We conducted the experiments like for the same input. I think we run for more than 10 times. Yeah, actually, let's say usually when you generate with diffusion model, you have a random noise. So you have not only the structure proposal, but also let's say a Gaussian noise. This is how you can like make it have diversity. So does this answer your question?
entirely sure. So it sounds like you say that every one of your predictions came from 10 samplings, and then you like average out.
No, I mean, for running the experiments for more than 10 times is because we want to show is like the result is statistically stable. So instead of random from one single pass,
But there is some amount of random prediction.
Definitely. Like even you ask the ChatGPT the same question, each time it can have different outputs, right?
Yeah.
Yeah.
So have you like quantified the spread in terms of the distribution that you're getting from, say, structure to property, or even just
Yeah, we'll show you in the experiments. Yeah. Oh yeah. I think is almost done. So I've already talked about this. So let's see the experiments. So basically, we want to show that the tool selection patterns vary based on the different difficulties. So for challenging tasks, it may select different tools than tasks with like easier difficulty levels, right? And also during the stage, the tool preference also change, which means like this is an iterative process, right? So you can, let's say from iteration 1 to 5 is early stage, 6 to 10 is mid stage, and 11 to 15 is late stage. And during this process, it's relying less and less on the knowledge base and more on the memories and so on. And also, like this is a success rate over iteration, and it increased with the iterations, which means that this iterative refinement is helpful compared to just a single pass rate, because those feedbacks can help. And also, we compared with or without tools, so and compare it with different models, and in all those cases, you can show that like with those external tools and resources, it can help with the generation process. And this is about the diversity. Like with tools and without tools, you can see the element distribution significantly changed. So the diversity of the generated models is improved compared to without tools. And this is so because the model can generate the reasoning process, it improves the interpretability. And also you can have some constraints in your input prompt. So which means you can also let your model, let's say, to avoid some elements or include some elements if necessary. So to summarize, so basically we found that our model can successfully explore towards the properties and generate materials chemically valid and diverse, and the reasoning behind the proposal is provided, and also it can handle real-world constraints in plain language. And lastly, so as the research of agents is very important, we also started an open source organization, so called Foundation Agents, so which is, you can check this link. So basically, we want to create a open source community for researchers all around the globe to collaborate on topics we are interested in. So you can check our survey paper and also check this website. Yeah, thank you.
There's time for one quick question, then you take them offline.
Yeah.
So
So especially for some materials properties, they are very sensitive with the theoretical level, how they were obtained for the band gap. So in this case, how also I think for the different database like Novak or Project, they were obtained with different theoretical level. So how did you deal with this inconsistency in the theoretical level of your data set?
I think we didn't consider that. We actually just run the experiments with different data sets to see how it performs on each individual data set. Yeah, yeah. So we're not like combining them together as a one whole. Yeah. No, we train our own diffusion model. Oh, yes, yes. Otherwise, it cannot utilize the generated proposal rate. Yeah, yeah.
Yeah, thanks to speaker.
Thank you.
And then if you have any questions, you can put them down. You're all tomorrow for about